So we have now the last presentation of the session. So please join me to welcome Professor Leif Christensen in the presentation about AI for long-term subsea missions. Thank you very much.
Hello. Yeah, thank you, Mr. Chairman. Yeah, we have heard a lot on now on terrestrial robots and also in the air. Now we are going a little bit in subsea. I just want to highlight just a few methods and systems and also one field trip, because it's I will not be able to list or have a complete list of AI methods and what you could do or what we are doing. So just a glimpse. I'm heading the underwater or the Maritime Robotics department at the German Research Center for Artificial Intelligence. And we are a public-private partnership of some German states, some universities, and some companies. You can see here. So here you see some of the systems we developed in the past for having prototypes or sensor carriers to do research on autonomy for subsea applications, starting with subsea crawlers and teams of subsea autonomous underwater vehicles, subsea resident AUVs that should live in an offshore field, for example, in their own docking station, doing their inspection rounds, more specialized systems or sensor heads that we did together with Atlas Electronic, for example, combining sonar systems with camera and laser line systems. And also the struggles that we have to making things small. So there's a mechatronics side to the autonomy research that we do. Okay, stated here, this would tell you we are not talking about strong AI for sure. For us, it's a tool that we would want to use to model things, to make things easier. And some examples I just want to show here. For example, if you have heterogeneous missions with different, so you want to have the sensor coverage, you have different sensors on several systems, you have to plan which agent takes what role and at what time, and maybe they have to interchange something in between, and this whole spatial temporal planning, something that where we can put AI to use and to come up with a plan and a task decomposition to be able to also autonomously have teams working together. Unfortunately, I cannot go into the details, but in the end, we are using a lot of these behavior tree-based mission modeling and uses for execution of these models. But we are at the beginning of this, right? Right now, the tasks are really simple. And we are doing research on this. It's not that we just say, okay, just use this, and then you're good to go with your heterogeneous robotic team. Another example we already talked about is the environmental representation is something that is reoccurring in heterogeneous systems. So all these agents have different ideas. They do SLAM, maybe they have an idea of the surroundings. Then you have maybe you have some this motion planning parts, you have physics, and all these have to work on the same environmental representation, which in the ideal case needs to be consistent. So we developed this Enviro method. In the easiest form, it is a map, but it could be much more, right? And you can define mathematical operators on this Enviro representation to get the information that you need or combine information that you need. And that is something that we work on. We have here's an example of an environmental representation, then visualized, for example, a multi-level surface map of a parking garage, where you can then say, okay, I want a traversability map of this, or I need some semantic annotations for certain tasks. So that was early on. It's quite a few years ago, but still we are using this Enviro representation for a lot of our research and systems. Yeah, I will skip over this. You most likely will know that if you are in uncertain environments, you will need to have probabilistic methods to act in this. You cannot say, okay, first I need the ideal and perfect representation. You will deal with all sorts of faulty measurements, faulty representations, degradation of your system. So you need these probabilistic methods, which are quite standard now. But I wanted to, no. Okay, let's see. Yeah, highlight one where we put this to use. Then this is one project for under ice exploration. It's also space related. The far vision is to go to icy moons, and NASA is working on this. The ESA is starting to do something in this direction. We are working together with the DLR also on another, this is the OREX project, but also on the triple projects project line. And the idea is in the far future, we want to go on these icy moons, for example, the Europa moon or Enceladus, because they know that there's an ocean under a thick layer of ice. And when they are looking for life, this is one of the maybe most promising places to look for. But this has a lot of challenges, right? You have to first go there in the first place. You have to land on this icy surface. You have to drill through 10 kilometers of ice, maybe, or multiple kilometers of ice, and then deploy an underwater drone that is able to look for life, because they know from that there are these black smokers, for example, that developed on the Earth without contact to the surface, and they found bacteria there. So and they know that there's organic material from eruptions on the surface of these icy moons. So they think, okay, maybe we want to go there. And so we did some research on how could we navigate under kilometers of ice without any infrastructure there. And so we are talking long-term autonomy. These oceans will be like 100 kilometers deep. Fortunately, they have a pressure similar to the deepest spaces on Earth, like it's just a tenth of the gravity. So we have like 100 kilometer, but 10 kilometers analog pressure on Earth. So that is, you can handle this. We have been in this depths before, but you have to take into account that your system will degrade for sure. We don't know really the surroundings, so we don't know if the hydrodynamic modeling will still work there. So we have to apply AI for this. Let's see. Okay, that is just a typical model would be a Fossen model, for example, from our Norwegian colleagues. It's often used, and this is quite standard. But we have quite some unmodeled effects. We can have some physical modeling beforehand, parameter identification, and then we have to take care of all these unmodeled effects, which become larger the longer you are on your mission. And the idea is here, for example, to have some long short-term memory networks learning this and being able to adapt during a mission for structural damage, or if the environmental situation is different than you have foreseen it, or other unforeseen effects. And we'll do all this in Z2. Here's one test where we had one of our AUVs in different configurations to simulate change. And in this case, for example, we attached something or we removed the hull. You could lose your hull, or one thruster is degrading. And I don't want to go into details, but you can just see, okay, there's a drop in how confident you are in your model and how good your model is working. But it gets back, right? It can react to this online while doing the mission, and getting good modeling results again from this with this learning methods that work online. It is for us, it worked better. Both worked better than the physics-based models beforehand. Also because of the degradation. Okay, only 4 minutes maybe. So okay, it's just some challenges that we have and the kinds of navigation that we have to do. For example, after you melted through with your ice shuttle, you have to leave and you have like ice relative navigation. We are envisioned to set up an infrastructure that we already tested in pools. And we also started going in field trials with this to set up some sort of underwater GPS system that you can then find back, because you will have to go back and then report your findings. So we have to find this point again. There are all kinds of challenges with this where AI can help. And I just wanted to highlight. Okay, this is a system that we used for this kind of research. It's a deep length AUV with all kinds of sensors equipped. The computing power is much too strong for now for a proper space mission, but it's like a sensor carrier for testing and concepts. So, but we are working also with partners who have a lot of experience in making things space qualified and how to work with less computing powers. But right now we have quite strong computing power on the system. And we went to the polar circle here in the north of Sweden, to the Abisko research station, the Lake Torneträsk. And we had the help of the Swedish polar research community there. They helped us with their motor sleds. So we set up this tent. We had an under ice test here facility, this tent. This is how it looks like then when working in these conditions. We had also all the challenges that you need to set up such a structure, a lot of planning going into this, and it will be becoming even more challenging in the next, I think in 3 years. We are now planning to go to the Antarctica, to the Neumayer station, and try to use these systems first to go to subglacial lakes. You see here we had a not yet melt through the ice, but a few weeks ago, a team from the RWTH Aachen, they were in the Antarctic to test the ice mole, and this should all come together in the future. We are not talking 5 years, 10 years, but like for Enceladus, it's more like 30 years, but we have to start somewhere, right? Okay, that is over this. Some also talking about from this field test, we gathered a data set that others you could use to check and evaluate your navigation system. We have different kinds, like evaluated our own system with just dead reckoning. USBL, maybe I have to explain, it's an ultra short baseline system. So it's like an, you have a absolute measurement, but a very bad one going through the water column with all its changes, currents, salinity degrades. You have some layers so it's very inhomogeneous in the water column. You have to deal with this, but it's an absolute measurement. Also then, so the markers, once you want to dock again, and you have good visibility, you can use markers or magnetic markers. Also there we introduced some machine learning to use these magnetic fields to dock. Just wanted to say, okay, you can access this this data set, and we were able to have some 100-meter under the ice round, not very long yet, considering that we want to go like kilometers in the future, but we managed to go back to our docking station and then recharge and also stay in the water for a few days. And we are trying to like getting more and more and longer journeys and longer docking periods, so that we enhance on this. Yeah, thanks for your attention, and any questions would be welcome.